Picking up where we left off, we're going to look at problems 5 and 6. Okay, so on problem 5, we've got two log expressions over here on the left, so we're going to condense them by using the product to sum property, which we're going to really be doing sum back to product. Okay, so we multiply the two arguments together, so we're going to multiply this, think of this as m and n. Because we have one log base 2 on each side of the equations, we can remove those. All right, now to algebraically solve this, we're going to want to FOIL, set the equation equal to 0, and refactor. So let's FOIL. When all that's complete, we should have x squared plus x minus 6 equals 14. So we want to set the equation equal to 0 and factor. So let's subtract the 14. Okay, this is a pretty easy factor because the coefficient on x squared is 1. So you can use your factor sum chart. We're looking for factors of a times c, factors of negative 20 that sum to positive 1. You can list all the sets of factors of negative 20, but I think it's going to be the factors that are 4 and 5. Now we need to make one of these numbers negative, so when we multiply and we get negative 20. So the bigger number needs to be the positive one. So 4 has to be negative so that when we sum, we get 1. I set each factor equal to 0. Okay, at this point, before we box these both, we need to check them one at a time in the original problem. So let's start with the 4. Let's go back to the original problem. When you put 4 in for this x, you're going to add and get 7. 7's positive. The argument can be positive. When you put 4 in here and subtract 2, you get 2. 2's a positive number, so we're good. And this argument is already positive, so we're good. So x equals 4 is a solution. Now let's check negative 5. When you plug in negative 5 for this x and you add 3, you're going to get a negative 2 argument. We can't have negative arguments, so we come down here and we don't box, we lightly discard, still showing all our work, just to say that we've considered this solution, but it's considered this proposed solution, but it's not one. So we only have one answer here. So just kind of thinking of other problems we might see, it's very possible that you could get down here and neither one of these check back in the original problem, which means the answer then would be no solution. And just a reminder, if that were the case, no solution, you could either write the words no solution, or the mathematical symbol that represents no solution is that circle with that little line through it. Okay, problem 6. If I'm going to solve this log equation, I want to condense these two log expressions here. I have a minus, so that tells me I'm going to go from difference back to product. Difference back to quotient. X plus 7's on top and 3's on bottom. Okay, one log on both sides, we remove them. Because this argument is a fraction, I'm going to go ahead and make 7x plus 1 a fraction. I'm going to cross multiply, so x plus 7 has to equal 3 times 7x plus 1. Let's go ahead and distribute here. Okay, we don't have a quadratic equation. This should be easier. I'm going to subtract this 1x from 21x's over here, so I still have a positive x term. Just a 0. Remember, this is 1x. I'm going to subtract a 3. And I'm going to come over here and I'm going to trade sides. I'm going to put the 20x on the left side of the equation equal to 4. And to get x by itself, I'm going to divide by 20. You can change this to a decimal, or you could leave it as the fraction 1/5. Let's take 1/5 and check it before we box it. When you put 1/5 in and add 7, all I care about is knowing that that's going to be a positive argument. Good to go. The other place that you're going to want to put the 1/5 in is here. And when you do this math, I don't care what the answer is. I just know it's going to be positive. So this is a good solution. Okay. All right, so solving logarithmic equations using like bases. We have 6 examples here. So let's go to solving logarithmic equations with a different strategy. Okay, so just kind of look over the steps for using this strategy. So maybe that light will be better. All right, notice that in these 4 examples right here, as they compare to the last 6 that we did, that not every single term in this equation has a log in front of it. So if I don't have a log over here, I can't remove logs from both sides of the equation. So when that's the situation, we have to use a different strategy. Notice in example 2, there's no log in front of 2, so it's not like I can just pick and choose to remove one log from one side of the equation. So, and then over here in example 4, this term and this term both have log in them, but one doesn't. So I can't use the strategy that I just used for the previous 6 to solve these. So what you want to do is when you're solving logarithmic equations, kind of inspect the equation. You know, if you need to move forward and go, okay, how do I solve this? Well, first of all, you know, inspect the equation. Does every single term in that equation have a log with it? Because if it is, then we're going to use method 1. If even just one term in that log equation doesn't have log with it, then we have to use this strategy that we're about to do right here. All right, the steps are, let's isolate the logarithm. If more than one log, we're going to have to condense. Well, that fits this case. Look at number 4. We have a log here and a log here. We're going to have to use our product to sum, or backwards, sum to product property. We got to get just one log on each side of the equation. Then what we're going to do is we're going to take that log equation and rewrite it as an exponential, and then we can solve. And don't forget, we always want to check too. Anytime you're dealing with log equations and solving them, you always want to check the proposed solutions, because the restrictions have us consider that the argument can't be a negative number. All right, so what we're going to do here is I'm going to identify that I have one log equation. That's good. I don't have to use any properties. Okay, when it says rewrite in exponential form, that's around the world situation. If you remember around the world, let's change this log equation to an exponential. We start with the base, 2. We come around here, 2 to the 3rd power to make it an exponential equals x minus 4. 2 cubed is 8. Add a 4 to both sides, you're going to get 12. Before I box it, plug 12 back in for this x. Yes, I get a positive argument. I'm good. How do I solve this log equation? I can't remove the log base 5. Change this log equation to an exponential. This value is 25. Add a 7 to the 25 to get x by itself. Check 32. 32 minus 7 is positive, so we're good. We can box. Okay, let's look at number 3. I want to isolate the log expression, but we also want to make sure that we have a coefficient of 1 here. Well, let's get rid of this 4 first by dividing both sides of this equation by 4. So the 4's divide out nicely, and we're just left with natural log quantity 3x equals 2. You might remember that ln can be replaced with log base e, keep the 3x equals 2. Parentheses aren't necessary right here. I can't just remove the log base e because I don't have one over here to remove also. So what I do, change it to an exponential. So e squared equals 3x. To get x by itself, let's divide both sides by 3. This is an exact answer right here. So you can just leave your answer like this, or if you prefer to change this to a decimal, I think I have that somewhere. I do not. I think it's 2.4 something. It's a positive number. Let's check it. So x equals 2.4 something. When you plug it back in here, you are going to get a positive argument. So I'm just going to leave my answer exact as e squared divided by 3. Again, I don't have the decimal. I think it's 2.4 or something. You could change it to a decimal if you want. You don't have to. This is a better answer because it's exact anyway. Okay, example 4. I can't remove the logs because I don't have a log over here to remove. And besides, I can only remove, in that case, I can only remove one log from each side. But for this strategy, I can't have two logs. So I'm going to go ahead and use my log property where I go back to a product. Because this plus is here, I will be multiplying this argument and this argument. I'll distribute x in my next step. Okay, so what's the base? Well, if I'm changing it to an exponential, so right now we kind of have this going on. If I'm going to change it to an exponential, remember without a base, the understood base is 10. So I'm going to have 10 to the first equals x times quantity x minus 3. So next move, distribute the x in. Because this is a quadratic equation, we're going to set this equation equal to 0. I'm going to subtract the 10 here and put the minus 10 here. Ooh, I think I'm going to run out of room. 0 equals x squared minus 3x minus 10. Okay, factoring, do a factor sum chart. It's an easy factor because that coefficient is 1. It should be x, and I believe it's going to be minus 5 and plus 2. So these factors will give us the two solutions, x equals 5 and x equals negative 2. All I did was just set these equal to 0 and solve. Now let's check each of these in the original problem. Let's check 5 first. When 5 goes in for x, we're good. When 5 goes in for x, that's a positive number, we're good. When you plug negative 2 in for that x, well, you get the log of negative 2, so we can't have negative arguments, so our only solution is x equals 5. All right, so far we've solved exponential and logarithmic equations, and when solving each of those, we had two different strategies. So it's kind of good to go back and look at all the structures and why did we choose the strategy we chose? What was in the problem? What did we identify in the equation that determined that we had to use a certain strategy? All right, so let's use these techniques that we've seen to solve equations to solve some application problems. So we'll do the first problem together. Take a moment if you need to pause and read through the problem, get an understanding of it, and then we'll work it out. Right, so this equation models the population of Texas in millions. So A is measured in millions. T is measured in years. It's part of the exponent. T years after 2010. Okay, so what was the population of Texas in 2010? Okay, well, first thing we have to identify is that if 2010 begins when we're using this model, that means that for this question, t equals 0. I'm going to put that above it because I think I'm going to need this room. If it had asked me what the population of Texas was in 2015, then my time value would be 5, and I'd be using 5 for my t. So what was the population of Texas? We're finding A, because A represents the population, round to the tenths. Got it. So we're going to find A. So A evaluated at 0. That means when t is 0. This is not necessary. You can just do A equals, but this gives us information that we're about to plug in 0, okay, for the t. So A equals 25.1 e raised to the 0.0187 times 0. I really don't need a calculator for this. You can use it, but when you go to solve this problem without a calculator, you're going to multiply these two exponents together. The result is 0. That means e's power is 0. Well, any number to the 0 power is 1. So this whole part of the problem is 1. And then 1 times 25.1 when we're multiplying is just 25.1. So let's respond to the question then. The population of Texas in 2010 is, or was, I guess I should say, 25.1 million, if this was the equation or the model that we're using to predict that. In which year, so we're finding a year. So for this, we're finding in which year, so we're finding time. Will the population reach 28 million? So it's good to decode. So 28 million is your A value. So going back to the equation up here that we're going to be using, A will be replaced with 28. I still have 25.1 times E raised to the 0.0187 T. I'm finding T now, given the population. Okay, this throws us in the objective that we have been working with. How do we solve this exponential equation? Well, this was this was method number 2 on the very first page. This is method 2. I certainly can't rewrite with same bases. This is kind of ugly. So go back and look to see what that strategy was. If you want to attempt it on your own, that'd be great. Okay, at this point, though, I'm going to move forward. I want to isolate the exponential expression. So I want to divide both sides by 25.1. I'm going to trade sides. I'm going to put the exponential on the left times t equals, and I'm not going to go to my calculator and get a decimal just yet. I'm going to save all rounding to the end just to maintain, the value of the answer. It's ugly. Okay, so what did we do next? Well, we were told to, in that strategy for solving exponentials, let's take the natural log on both sides of the equation. Okay, the next step is we use properties to move this exponent, because we have a log function. We use properties. We took this exponent and put it in front as a factor. So I'm going to take this whole exponent and move it in front of ln of e. This is times. All I did was I moved it here. At this point, I want to solve for t. Notice that you have 3 things that are being multiplied. You've got this decimal times t times ln of e. So what I'm going to do to isolate t is I'm going to divide by these 2 other factors at the same time. Dividing by ln of e will divide out that ln of e. Dividing by that decimal will divide out that decimal as well. So over here I have to still divide by the same 2. Same also. And then this is, I'm going to put a little times there because it kind of blends together. I'm going to be left with t equals, okay, this is going to be very cumbersome. You might want to find this decimal value and then do divide by. Make sure to put this in parentheses when you divide by the denominator. Okay, here's your target answer. So in which year will the population of Texas reach 28 million? I would probably think about rounding that up to 6 and adding it to the year 2010. Let's see, to save time, I would respond with a statement. I would say the population of Texas will reach, because of time, I'm just going to just say it. The population of Texas will reach 28 million in 2016. Because it's asking me the year. So you always want to go back and look at the question and make sure you're answering the question. The answer isn't 5.847, but it helps us understand that the answer would be 2016. Okay. All right, we've got a couple other application problems down here that deal with compound interest. I'll do this one. This one's similar with just a change of numbers. The worked out solutions will be on the key. All right, using this formula right here, it says how long to the nearest 10th of a year. So we're finding time. I put a little question mark there. How long will it take $1,000 to grow to $3,600. 1,000 is your P, your principal. This is the amount you want. 8% is your rate, so we'll change that to 0.08. Annual interest compounded quarterly. Well, N represents the number of compoundings a year, and quarterly means 4. Okay. So I'm going to just use this formula, plugging in the numbers that I have. And then remember, the exponent is the product of N and T. I don't know what T is, but I do know N is 4. All right, stepping back, looking at how are we going to approach solving this problem. It's an exponential, not a logarithmic equation. So think about the two strategies we use to solve those. I can't get the same base, so these are just ugly numbers. I'm going to have to use strategy 2. Let's isolate the exponential expression first, and then we'll bring in ln on both sides. So to isolate, I'm going to divide both sides by this constant multiplier 1,000. Then what I'm going to do is I'm going to take this expression and put it up front. I'm trading sides. So I divide these out. Now coming over here, I know that I can simplify this. I don't think I'd change it. Well, maybe I would change it to a decimal. This will be a nice decimal to work with. I can divide these zeros out. That's like dividing 100 out. 36 divided by 10. Well, I think that's just 3.6. Okay. If it's a nice number that you get from a calculator by simplifying this, I'd probably write it down. Otherwise, something like this problem right here, I'm not going to find that decimal. Okay, so next thing we're going to do is we're going to bring in the ln on both sides. You could go ahead and calculate and compute this value and use that as a decimal. I think it's going to be I think it's just 1.02. That might minimize your work. Otherwise, you could just leave it as is. I think my rule of thumb is if I try and simplify this to a decimal, is it a nice decimal? If it repeats or ends, I might use that. Otherwise, I'm just going to use it the way it is. Okay. And then don't forget ln over here. So ln on both sides. Okay, we're going to use a log property. Because we brought the ln in, we can bring the 4t in front as a multiplier. And I want to say that this is 1.02. So I moved the 4t in front, and I went to my calculator and I got 1.02, and I have ln of 3.6 here. Okay, how do I get t by itself? I'm going to divide out the 4 that's being multiplied and also this log value. And then don't forget the 4 over here, and then the ln of 1.02. So the exact answer is this, but it's not really revealing to us what that time is. So if you go to the calculator, I think I got 16.2 years. If I rounded to the tenths like I was asked to, I think, well, it didn't ask me. But we're going to go ahead and round to the tenths. So it'll take a little over 16 years for our money to grow from 1,000 to 3,600 with that interest rate compounded quarterly. I'll leave this one for you. It's the same, just change the numbers. Okay, let's look at the last one, number 3. Maybe you picked up on the word compounded how often? Continuously. That's why we have the A pert and not this compound interest formula right here. So that's your keyword, continuously. So let's decode this problem. How long is what we're going to be finding. So we're going to be finding time to the nearest tenth of a year. Oh yeah, we were told to find it to the nearest tenth of here. How long will it take an $8,000 investment, that's your principal, to grow to double the amount? So we want A to be 16,000 if we're doubling 8,000. It didn't come out and straight up tell you what A was, but the words told us what we should be looking for. invested at 8% annual interest. So the rate is 0.08 as a decimal. So we're finding t in this formula, so we should know all other variables. So set 16,000 equal to 8,000 for p, and then you have e, and the interest rate 0.08 times the t we don't know. What kind of equation do we have? It's exponential. I can't get the same bases because those are ugly numbers. So I'm going to isolate the exponential expression. I'm going to divide both sides by 8,000 and bring in the ln. 16,000 divided by 8,000 is just 2. That makes sense because we're doubling. I'm going to put an ln on both sides, but I'm also going to do another step of trading sides. So yep, looks good. We want to get t out of the exponent position, so because we have a log function, we're going to put that in front as a factor. And I got the t here. And just bring this down. We want to get t by itself, so let's divide out these two factors that you're multiplying t by. So this is the exact answer, but that doesn't really reveal to me the amount of time it's going to take for 8,000 to double with these conditions. So going to your calculator, rounding to the tenths, I got 8.7 years. Again, just be careful with inputting fractions into a calculator. Make sure that you're dividing, and especially with the denominator, putting that whole quantity into parentheses. Otherwise, your calculator is going to take and divide natural log by 0.08 and then multiply that answer by ln of e. And that's not what we want to have happen. Okay? Alrighty, that's it.